Did you guys get negative 2.72 for the pOH? Yes? There are two ways to find the concentration of hydroxide. What are the two ways given the information that we have here? Yeah, we can use kW, right? What's the second way? You can take the antilog is what we call it. The 10 to the whatever is called an antilog. Okay? So a 10 to the x is called an antilog. So you're going to take the antilog of the negative of the pOH. No, you do it by using the inverse log button on your calculator. It'll be right above your log. Okay, so you'll see there's a 10 to the x button. And that's the button that we tell you in grade 11, never use this button, right? That's when everyone's trying to, like, you know, do 10 to the whatever. Don't use that button for like scientific notation, but you can use it here because that's what it's for. It's for finding the antilog. Okay, so why don't you try this second method, because that's kind of something new to do on your calculator. So you're going to have 10 to the negative, oh, except for that it was negative 2.72, so you're going to say positive 2.72. Now, do you see why we don't run across positive pOHs, or sorry, negative pOHs very much? Does that look like a reasonable molarity? Is that something we see on a daily basis? No, okay? These are sort of numbers that we just kind of threw up there to prove that yes, you can, the math will do it, but you won't end up with anything very much above 14 or very much below 0, okay? Sort of like 15 to negative 1 is kind of the maximum range. Okay, this is just going over what we've just talked about. Do we need to do anything with that? No, probably not. Blah, blah, blah. Does anyone care about how we get pOH plus pOH, pKw equals pH plus pOH? Does anyone care how we got that? Or are you happy just knowing it? Not sure? Okay. Do you want to just believe me? Or do you want to derive it through log rules? No, okay, skipping right along. La, la, la. So all you really need here, because we sort of covered a bunch of the stuff on the previous pages earlier, is you need to know that 14.0 is equal to pH plus pOH and pKw is equal to pH plus pOH. Hebden has a handy little conversion chart on page 138, which I have included here. Okay. So if you can't remember them like just sort of individually, you can memorize this little chart if it's helpful, okay? But if it's not helpful, and this is where you remember we just talked about this, yes? So the concentration of hydroxide, what would the hydroxide of the concentration be? It was the 10 to the negative pOH, yes? So if the pH is 4, 10 to the negative pH is 10 to the negative 4, which is 1 times 10 to the negative 4 molar. Now, this is the only part, again, where this gets tricky, is the sig figs, because if we look at our pH, how many sig figs in 4.0? 1 sig fig. Because it's a pH, yes? And so when you, because it is a pH, and so when you have your answer to hydrogen, it can have only 1 sig fig. So if the pH is -1, then hydrogen ion concentration is 10 to the negative pH. So it's going to be 10 to the -1, so that is 10 molar. And I don't know why I have an arrow there. Oh yeah, because we need it to correct sig figs. What would that be to correct significant figures? 1.0 times 10 to the 1 molar, or you could kind of write 10 molar, but that's not usually as nice. Yeah? Okay. So do you need a lesson in plugging into your calculator? Are you capable of doing that? That's good. All right. You can show your work either way. You can either write H is equal to 10 to the negative pH, or you can write H is equal to anti-log of negative pH. This is my favorite because it's shorter. Okay. And besides which, that's what it says on your calculator, so it helps you remember. So here is the table with all the information. If you want to go down from hydronium down to pH, you're going to use this one, right? If you want to go down from hydroxide to pOH, you're going to use negative log. If you want to go up from pH to hydrogen, you use hydrogen is 10 to the negative pH, and so on and so forth. Yes? And then, of course, hydrogen and hydronium are connected by kW. And lastly, I think I have one more highlighter color. Yes, I do. pH and pOH are connected by pKw. Is good? Okay. Okay, there's some exercises we're just going to skip. There we go. So we're now on 4.2D, page 86. A solution is neutral when hydrogen ion is equal to hydroxide ion. Does that make sense? Okay. A solution is acidic when hydrogen ion concentration is greater than hydroxide. Yes? And it is basic when hydrogen is less than hydroxide. I'm going to try and do a magic trick. I don't know if it'll work because you guys are kind of too smart maybe, but I'm going to make a magic trick and make you forget this by the end of this. Okay? Okay, we'll see if my magic trick works. Sometimes it does, sometimes it doesn't. Okay, why does pure water have a pH of 7? This question is actually misleading. Pure water has a pH of 7 only at 25 degrees Celsius. And that is the temperature at which the kW is 1.00 times 10 to the negative 14. Okay? What happens to K values when you change the temperature? They change. Yes? Okay. So here's some pure water at room temperature. So in pure water at room temperature, we have our hydrogen times our hydroxide is 1 times 10 to the negative 14. Could you figure out what the hydrogen ion concentration is just from here? What's the hydrogen ion concentration just from that equation? Chat with your partner. Could you figure out hydrogen ion concentration in pure water? All right, so hopefully you realize that hydrogen and hydroxide in pure water, every time it dissociates, you get 1 hydrogen and 1 hydroxide, or if you write the autoionization in the more expanded method, you end up with 1 hydronium and 1 hydroxide. Either way, it is 1 to 1. So what that means is that hydrogen and hydroxide are equal. So we could actually replace the hydroxide with a hydrogen, and we end up with hydrogen squared is equal to 1 times 10 to the negative 14. And if you take the square root of that, you end up with 1 times 10 to the negative 7. And then if you take the negative log of that, what do you get? 7, yes? And pOH will be 7, and hydroxide will be 7, because everything is equal when you have pure water, right? Okay. So that's where that pH of 7 being neutral comes from. Everybody's 777. Now, here is a little table showing the temperature dependence of Kw. All right. So how about we figure out, how would we figure out the hydronium ion concentration at 0 degrees Celsius? We have a Kw at 0 degrees Celsius. Remember, K changes with temperature, so it's no longer 1 times 10 to the negative 14. Now it's 1.1 times 10 to the negative 15. How would you figure out hydronium ion concentration there? I think you're right. What would you do? You would take the square root of it, yes? Just like we did before, because hydrogen, all right, we've still got Kw is equal to H times OH. And if you want to call them X, right, we have H2O, H plus, OH minus. If they separate, you get X and you X, so that's equal to X squared, okay? And so we could go through, and why don't you go through and you figure out the hydronium and the hydroxide, okay? Yes. It's always pure water, so it's always 1 to 1. Yeah? How is it neutral? It's not what? No, it's not. So when you taste your water and it's been in the fridge, it's maybe at 4 degrees Celsius, right? So what does it taste like? Does it taste like water, or does it taste like acid, or does it taste like base? Tastes like water. Yes? Because what has happened to our equilibrium? Our kW is smaller. If our kW is smaller, what does that tell you about that equilibrium? Compared to 25 degrees Celsius, it sits more to the I got a smaller number here. If I have a smaller number, do I have more product or do I have less product? I have less product. So at 0 degrees Celsius, this equilibrium sits more towards the left. Yes? At higher temperatures above, we have a larger, and so this equilibrium will sit more towards the right. But if we look at this, and in fact, why don't we do this for a moment here, and we'll figure out, is the autoionization of water endothermic or exothermic? Why don't you see if you can figure that one out? So at a higher temperature, you have a larger kW, and therefore your hydrogen and hydroxide are larger. Is this making sense so far? Okay. And if that's the case, an increase in temperature caused a shift to the whichy way? Right. So where is your heat term? The heat term is on the left. And therefore, is the autoionization of water endothermic or exothermic? Endothermic. Yes. I'm going to go back up in just a second. Yeah. Okay. So we carry on here. What is the pOH of pure water at 0 degrees Celsius? What is the pOH of water at 0 degrees Celsius, this one right here. Pardon me, 14 minus that. So is it 14 minus 7.472, which would be 6.528. Is that true? Oh. We have pure water, right? Do you remember how I told you I'd make you forget that in pure water, concentration of hydrogen is equal to concentration of hydroxide? Do you remember when I told you that magic trick I was going to do? Did I just do that magic trick? Oh, look at that. Because if hydrogen and hydroxide are equal, then what must you know about pH and pOH? They must also be equal because you're taking the negative log of the same number. Yes? Yeah? And the reason is that if you have kW, and if kW is changing, then what else is changing? If kW changes, concentration changes, yes, but pKw also changes. It is no longer 14. So my pKw value would be 7.472, 14.944. Yes? So your pKw changes. So pH plus pOH does not equal 14 unless you are at 25 degrees Celsius. Okay? Yes, yes, yes. Okay. And you could go through and do this for all of them, and you'll see that your pKw is different all the way down. Right? There's our magic 25 degrees Celsius. Hydrogen is equal to what? That's a total typo. It shouldn't be 7 times 10 to the minus 7. What should it be? 1 times 10 to the minus 7. Oh my gosh. 1 times 10 to the minus 7. There we go. Oh, that's terrible. Anyway, nobody caught me on that one. And it's like, okay, 7's all the way across. So temperature changes the pH, but it also changes the pOH by exactly the same amount. Changing the temperature changes the hydrogen ion concentration, but it also changes the hydroxide ion concentration by exactly the same amount. Yes? And so the two remain equal. pH still equals pOH, H still equals OH, but they don't equal 1 times 10 to the minus 7, and the pH and pOH do not equal 7. They equal something else, but they are the same as long as it is pure water. Okay, we're not going to be looking at any instances where we're changing temperature and concentrations because that's just too confusing. Okay, so write a formula for how to calculate the hydronium ion concentration in pure water. What would that formula be? H3O plus equals the square root of Kw. Yes. Okay. What is true about hydronium and hydroxide in pure water? They're the same concentration. So is pure water acidic, basic, or neutral at 50 degrees Celsius? So let's take a look at 50 degrees Celsius. There's our 50. Is your water acidic, basic, or neutral? It is neutral, okay? Even though the pH is 6.631, that is neutral at 50 degrees Celsius because they equal the same. So neutral pH at 50 degrees Celsius is 6.631. Okay, so I'm going to leave you guys with some exercises to do. Let's see, you can do page 88. Actually, I'm going to write it on the board. Let's make sure we're not forgetting about that stuff. You are going to do page 49 to 50, number 6. And finally, page 71. Okay. Hi. Oh, did I? I'm so sorry. Oh, very likely. That's fine. 9, 10, 11, 12, 13 and a half. 14 and a half, you're right. Sorry? Can I go back up? Yes. You wanted, no. That one? Yeah. Which part? This part? Oh, the last part. The last part? There? Yeah. What? Neutral. Oh, neutral pH. It says up there. Oh. if you don't want to read upside down. Okay. Good. That's okay. Thank you so much. Yeah. Yes. No, technically it's neutral, but the pH is not set. Yeah. Yes. Tricky, hey? It's a mind game. Yeah, exactly. You don't often have like more, but yeah. And yes. About one. I know, right? Okay. So this is one more. Yeah. Yeah. One, but you know, if you have more, you can do it. Yeah. So let's say you had sodium hydroxide. More soluble. Yeah. 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 And this is just kind of because it turns out most of the people will be like to go through it in different times so that you're like not get crazy. Everyone's like,
just like so tired today. Yeah, well, we're almost done our unit. We might finish tomorrow. Yeah. Well, it better be just one because we've got only 4 more weeks after this week. Oh, it's just, oh. Atoms and periodic runs and stuff. Yeah. Yeah. And you're like, crap, I don't know any of this stuff. I did not know any of it. Yep. Yeah. But I was like freaking out. I'm like, how many other units do I not know that I have to learn? I really wish that I had been able to figure out how to do it kind of in English class here. Yeah, well, you know, like the always wrong what we do. So. And at first I decided going being very oh, I don't know if right. So right. I didn't figure out right. And I actually wanted to AP. Yeah. And then I wanted to try to get it rearranged, but I couldn't. Yeah, something else. Yeah. So I thought yeah. It's mostly okay. Yes. This one's gonna be busy for me too. I gotta mark all my grade lines labs and make sure that everything's ready because our report card marks are due soon. Yeah, you have capstone. I don't understand why capstone isn't due like after AP. Wouldn't that be great? Yeah. I know. I'm like, why are they putting all these things before AP? They use them after AP. Oh well. Everything's just gonna be like, whoa. Almost there. All the big things are like this one. Yeah. Have a good one.